Hello and welcome to CAD Modeling Shear Driven Cavity Flow tutorial. This video will give you a preview of how to create a geometry to generate a mesh and to compute a steady CFD simulation using CAD Modeling. In this case, we want to perform a computation including a viscous fluid contained in a cavity. All the walls of the cavity are stationary excepting for one which is sliding and set the fluid in motion inside the box through entrainment. This is a well-known academic case for which published results are available. Please refer to the PDF tutorial if you need additional details. First, I will show you how to use basic functions of the CAD Salome module entitled Shaper. Second, I will mesh the CAD model using Mesh module. Third, I will set the CFD case using CAD Modeling software. And finally, once the computation is done, I will check the results using PeerView software. Let's now create the 3D model. For this tutorial, I advise you to create a folder in which all files, including the 3D model, the mesh, and the case, will be saved in. Once this is done, you can open Salome, create a new file and save as, let's say, cavity mesh file. Save it. Then open the Shaper module. Shaper module is a CAD software, so you could use it as standard CAD software by creating, in our case, a part. This is part 1. Then once part 1 is created, you could create sketch, selecting the plane you want to draw on. In our case, I select X and Y plane. Then I will draw rectangular shape. Here is the shape. I will add some length by selecting here the function length. Remember, our cavity is 1 meter per 1 meter. So here you have the cavity shape. You could validate the length and validate the sketch. As soon as the sketch is done, you could use extrusion function, select the shape and add the size 0.01. And now the cavity is created. Before moving forward, I highly advise you to create groups of faces and edges in order to set further boundary conditions using CAD Modeling. In order to do that, select Features, Group, and now we will create 4 groups. The first one is called Stationary Walls, which includes all stationary walls. In order to select multiple walls, you could use Maj key on your keyboard. So this is stationary. If you want to rotate your model, you could use Control keyboard and right mouse button. Here are the 4 stationary walls. You could validate and move to the next group, which is sliding wall. Sliding wall is this wall here. Wrong wall. Here we are. The third group is called Symmetry Walls. And the symmetry walls are the following ones. This one and this one. And the fourth group concerns Z edges. So we'll call it Z edges. Select the type edges here and select all edges following Z axis. So in our case, it concerns this edges, this edge, this one, and the latest one. This one. So you could validate, and now you have 4 groups. So as soon as this is done, you could move to the mesh module to create your mesh based on this CAD model. We will save in order to make sure that if there is a problem, you could recover your work. Creating the mesh is quite simple in all cases. First, you need to select this button, Create a Mesh. Then select the geometry. It is extrusion _1_1. Then proceed to the following settings. Select 3D tab, algorithm, hexahedron. Regarding 2D algorithm, you could select quadrangle mapping. And regarding 1D algorithm, you could select wire discretization. You could also add hypotheses here by clicking here, basic, select number of segments, then add 50 number of segments with type of distribution, equidistant distribution. This will apply a general law regarding every direction. So now you can apply and close. If you right click on mesh 1 and compute, you will see the mesh, but this is not the mesh we expected, because regarding Z direction we have 50 different segments, which is too much for our geometry. We just want one segment here. In order to do that, you need to create a sub mesh here by clicking on Create Submesh. Select the geometry. Now we will select the Z edges group we previously created. Under 1D tab, select Wire Discretization Algorithm, and then create another hypothesis, number of segment options, then type 1. This will create only one segment following Z. You could apply and close. Go back to mesh 1, click right on it, then clear and compute. And now we have the results expected in our case. As soon as this is done, your mesh is done. Then you could save your case. You could also rename the mesh by renaming it Cavity Mesh, and you could also export it using export option and MED file. You could also name it Cavity Mesh, and now you're done. As soon as the mesh is done, we will be able to set the cut Saturn parameters for our CFD case. In order to create cut Saturn files, you need to type the following command. You previously opened a terminal in this folder you created before, Shear Driven Cavity Flow folder. You could type cut Saturn create -s Shear Driven Cavity Flow -c case 1. You could press enter, and as you can see, a new folder appears with case 1, a mesh folder. You could also copy the previously mesh into this mesh folder. And under case 1 folder, you will have data, result, and sources subfolders. Data will include a setup file, which is very, very important for CAD Saturn. All results will be saved into this folder, but now it's empty. And all sources file you need to perform CFD cases are located here. If you need further details about sources file, I advise you to watch the other video tutorial. So now this is done, we will perform the CFD settings. Now we will open graphic user interface of CAD Saturn. In order to do that, you need to move into the data subfolders. So in our case, we'll move into data case 1 data. Then we will open CAD Saturn and set the cases. One thing that is very important, the case is called setup.xml. You could save it at every time you proceed to a change. You could save it in order to recover your work if there is a problem. So in our case, we will save it. Then you could move to the mesh tab and we will import the mesh we previously created by clicking here on add a mesh. Select cavity mesh. Then we will proceed to a pre-processing computation in order to check all boundary zones we created in Salome. So you could run computation, select one number of processes and threads per processes, which is totally normal in this case, save case and run calculation. So now once this is done, you can select standard computation, then move to boundary zone. Under the add from processor log, you could open this window, go on case 1, results, then select pre-processor log. And as you can see, all the groups we created appear here. So we have the sliding wall, stationary walls, and symmetry walls. So now this is done, we can move to calculation features, select Eulerian single phase, incompressible. You don't need to add turbulence model. So in our case, you could select laminar flow. Don't need to add thermal model either. You could directly move to volume conditions, select initialization and physical properties. Don't forget to save your XML document. Go under all cells tab. Here the density should be 1 and the viscosity should be 0.001. Initialization regarding velocity is 0.1 following x direction. And you will be done. The volume conditions tab, you could save your XML document. Regarding boundary conditions, make sure all boundary conditions are well selected. In our case, remember there is a symmetry wall, so that means BC3 should be symmetry. So now this is done, you can also go back here and make sure that BC1 is sliding wall, and if you go on BC1 you could select sliding wall then add a velocity following u, which is 1.0 meter per second. BC2 should be a smooth wall and BC3 is symmetry, so you don't need to add additional parameters here. You could save your XML document, move to time settings, select time varying option. You could change your CFL number up to 8. Then, if needed, you could also add number of time step up to 400, which I advise you to do. Now you could move to numerical parameters, select equation parameter. Regarding velocity, you could change the solver choice, and I advise you to select not solver choice but scheme and select center. You could untick slope test. Now this is done, you can save your XML document. Regarding the post-processing tab, you don't need to add further parameters here, but you could add, if needed, monitoring points. I will add 4 monitoring points, just like in the PDF tutorial. So the first one is 0.25, 0.5. Second here it's 0.5, 0.25, 0.5, 0.75, and the last one 0.75 following X and 0.5 following Y. Now you can save your XML document. You could move to surface solution control, untick stress and Y plus, which is not relevant for our case. Then move to profiles, and you could add 2 profiles. In order to configure profiles, we will set it as the same as the PDF tutorial advise you to do, which is here in our case the file name should be X velocity following Y axis center line, Y axis center line. So velocity here, okay, number of points, let's say 50, select velocity. Then you need to define it. This is the variable. Variable here is S, and if you go to under example tab, you will see that S is a parameter that is always between 0 and 1. So that defines the profile. You could do the same for the second profile regarding x-axis, which is y velocity under x-axis, center line. Set it. This time S should be here and y equals to 0.5. Now this is done. You completed this part. You could save your XML document, then proceed to the computation by clicking on Run Computation, and you could run your calculation. This window appears, and if you want to follow the convergence of your computation, you could click here for any computations. Here the computation is quite fast, so you don't need to see it, but we could open it for you. And And as you can see, you have here the residuals values. It's a very convenient tool and I advise you to use it. So now let's move to post-processing phase using ParaView. ParaView is a powerful post-processing tool, and now I will show you the results following our case. Once your results are loaded, you could click on the eye to have a glance on the results. If you want to see a cleaner result view, you need to add a filter under this tab, select alphabetical, then you select cell data to point data. It will give you a cleaner view of the results. Here, I ask you to scale to visible data range in order to have the minimum value and the minimum value of your variables you want to plot. So in this case, velocity magnitude is plot. You could also select pressure if you want to rescale it. And in all cases, this is the same results we have in the PDF tutorial too. So go back to velocity. Another interesting thing we could also do with ParaView is to plot lines. So you could add a layout, select line chart view, then we will load monitoring points, and let's plot, for example, the pressure values. You could apply. Here's the spreadsheet including all values. You don't need that. You can untick T, and as you can see here, it's the number of iteration following x-axis, and following y-axis it is the pressure values for each probes. So this is relevant. You could also plot, if you want, the profile you previously set. You just need to load the file you want to plot, here profiles, and select, for instance, x velocity. Here you have the values. I advise you to untick X, Y, Z, and S. Then make sure to select here Y values. And here you have the velocity components. So you can plot multiple lines here regarding what you are looking for. This concludes this video tutorial. I really hope you enjoyed watching this video. I highly recommend you to keep tracking CAD Modeling updates by checking on our channel or social media pages to get the latest news. Thank you for watching.